Okay, let me finish up 7.5 in this video after I get everything good here. Yeah. Okay. So I'm kind of skipping around, of course. I'm skipping example 2. This is about like railway cars that are attached with springs, and now there's no walls at all, but we can just imagine that there's a wall on the left and a wall on the right, and then like springs with spring constants of 0. So this can be sort of like completely free floating, just with we imagine that there's imaginary walls and imaginary springs with a spring constant of 0, and we can handle that example. Um, there's nothing too special about example 2. I'm just kind of skipping it in the interest of time. It is a 3x3 system, but the procedure for 3x3s is the same as 2x2s. It's just more work because it's 3x3s, but we know how to find eigenvalues and eigenvectors for 3x3s. We've done it many times, so you should know how to do this. If you can do a 2x2 and you can do eigenvalues and eigenvectors of 3x3s, then you're fine. So let me skip to this part. Forced oscillations and resonance. This is on page 431. This was all previously, the discussion in this section was, like if I cover up this F, that's what we were doing, because we were assuming that there was no external force acting on the springs. All of this analysis is just sort of like analyzing, if we have this picture, let me skip back to this picture. If we have this picture and maybe I start the masses wherever I want so that I can start them off so that they're not in equilibrium, and then I just let them go, we have been analyzing like what happens, like what trajectory do they take if I sort of place them however I please initially and then let them go. But that's all we're doing. There was no external force before. Now there is. So, blurry. Yes, good. So instead of just what was on the right before, when there was no external force, this was all of the force. But now that there is external force, I'm just going to add this F that's the external force. So that's, this equation is easy enough to understand, line 28. Just as we did before, I would like to multiply both sides by m inverse to solve for x double prime. And we can imagine that we did that. I did m inverse, and so m inverse times k is just a again. And let's imagine that m inverse times big F is little f. But we never really said what big F was, so we don't have to worry about what little f is. It's just some vector that's representing external forces. We are going to be pretty limited in our discussion of this. We're only going to really handle as long as this vector f takes a very particular form, like a periodic, specifically cosine function. So we're assuming that little f is like a constant vector, big F naught. This big F naught doesn't really have anything to do with this. Well, I shouldn't say they have nothing to do with each other, but they don't, the relationship is not simple. Big F is just some vector, a constant vector specifically, times this cosine. So it's like a periodic force that we're exerting. In that case, as usual, we are going to guess a particular solution. And this is like a common theme, because I would not call this a homogeneous system anymore. we were dealing with homogeneous systems. It would be homogeneous if this f would be gone. Um, so what do you do for a non-homogeneous system? You, first of all, you get the homogeneous part, and then you guess a particular solution to the non-homogeneous part. So that's what we're doing. And if our f, be unblurry, there we go. If our f has like a cosine involved, then we're going to guess that our particular solution also has a cosine involved. And this is, roughly speaking, this is a common theme. We generally guess that our particular solution should take the same form as the non-homogeneous part. So if the non-homogeneous part is a cosine, then we're going to guess a cosine. And we're going to guess that this is times some vector c that is yet to be determined. So why is this a decent guess? Well, the only real answer to that question is because it works. But why does it work? Well, I would like to plug it in. So actually, let me maybe go back to here. It's a little blurry. Yep. So x double prime should be ax plus f. Where little f is actually this. So let me write that instead. F naught cosine omega t. So that's the equation, and we are plugging in this. So xp double prime, actually let me put vectors on everything that's a vector. So okay, so I am taking this derivative. So c is a constant vector, so I'm just doing the derivative of the cosine part, so it's going to be negative omega c sine omega t. And then the second derivative, I'm doing the derivative of this. And again, omega is a constant, c is a constant. I'm just doing the derivative of sine omega t. So there's going to be another omega. Derivative of sine is cosine. That's an omega. Right? So that's what they're saying here, that the xp double prime is negative omega squared c cosine omega t. And then the book doesn't show a lot of work, so because I'm an active reader, this is what I'm going to do. Let's check. I want to put this in here, so let me put in the second derivative. Negative omega squared c cosine omega t equals AXP, so A times, and then let me replace XP with what it is, right? So C cosine omega t plus, so I'm still copying this down, I'm just replacing things, F naught cosine omega t. Everything has a cosine omega t on it, so cancel, cancel, cancel. And then, right, I'm trying to justify this line. That's what I'm really trying to do. And I think I'm almost there. So I crossed off these cosines, And yeah, let me just, I think I'm going to move the F naught to the left, and I'm going to move this to the right. So I would get negative F naught equals AC plus omega squared C. And I'm almost there because this says this. And I'm just going to do a little trick that we have done before. Of course, it's very tempting when I see something like this to factor out the vector C, so to speak. But what I would get if I just wrote that is technically nonsense. I'm very deliberately leaving myself some space here because what I'm writing right now is nonsense, because I can't do A plus omega squared. A is a matrix and omega squared is just a number. It's a scalar. You can't generally do a matrix plus a scalar. However, if I write an I there, I is representing the identity matrix. Now this makes sense. I can do a matrix plus a matrix, and what the other reason why it makes sense is because I times C is just C. So it's almost like this I isn't doing anything except serving the purpose of making sure this expression makes sense. So that's what we do. And that is how we can solve for the vector C. Okay. Let's see this maybe in practice. Example 3. We take the same system from example 1, which, if you remember, was like this. Where is the... Well, okay. It was x double prime equals ax. Yeah, okay, here it is. X double prime equals ax, where A was this matrix. So for example 3, I'm going to take that, except now there's going to be an external force. So x double prime is going to be A times x. A is the same matrix. It's these numbers, negative 75, 25, 50, negative 50. And those numbers are here again. Those are the same, right? Yeah. Okay, good. And except now there's going to be an external force, and the external force takes the form that we wanted it to take. This is an external force that takes the form like it's a vector times a cosine. So we're here. What do? The substitution x equals c cosine omega t leads to the equation blah. So why is that? Let's be active readers. Okay, maybe this is going to be easier to check than I thought. Let's still check it. I think this is just this equation. Yeah, sorry. This equation. Let's see here. I believe this is the matrix A plus omega squared I, right? I just took this matrix and I added omega squared down the diagonal. That's how I would do A plus omega squared I. So that is what I would get. So that matrix times C equals negative F naught. F naught was just this vector. Okay, so I could check it without really writing anything. Good. What happens, this is a 2 by 2 system. Right, it's not a very nice one because I have variables inside of it, but I can solve it. Right, like, yeah, maybe this is, what is the nicest way to solve this? Maybe with Kramer's rule, actually. So yeah, let's talk about that. So we are solving this times C equals this. If you remember Kramer's rule, I can, so if the vector C is like C1 and C2, I can solve for C1 it's a determinant over a determinant. The determinant on the bottom is just the determinant of this. Sorry, I'm writing so small, but it's just the determinant of the original matrix. The determinant on the top is going to be the original matrix with one column replaced. I'm going to replace one of the columns with this vector. Which column do I replace? The first column, because I'm doing C1. So it's that. And let me, oh boy. Yeah, why don't I try to really do this? See how much trouble I get myself in. So this would be, the determinant on top is easy because this is 0 plus 50 times 25, assuming I can actually do 50 times 25. I believe it's that. And okay, I'm not in too much trouble yet because that agrees with the numerator that the book claims. Let's see if I can deal with the denominator. Yeah, this one's going to be ugly. I got omega squared minus 75, omega squared minus 50, minus 50 times 25, which is 1250. Yeah, really going to need to work on not writing so far to the edge of the paper. Yeah, that looks terrible. Sorry. Okay, little bit better. So I imagine if I take this and I simplify it, I'm going to get the same blurry, good. I'm going to get the same denominator that they got in the book. So actually, maybe I will skip that part. I encourage you at home to check that if you multiply this out and factor it, you get this. I also encourage you to check the value for C2. You can get C2 the same way. It would be a determinant divided by another determinant, except for C2 on the top, you would take this matrix and replace the second column with this instead of the first column. And you would do that, and I encourage you to check that you get this. So that's how this can be done. You can solve for your C1 and your C2. And Right. Where do we go from here? Um, this example is partly an excuse to talk about resonance. So resonance, yeah, so it's dangerous for me to talk about this because I'm not a physicist, so I always feel like I'm at risk of saying something stupid. But roughly speaking, resonance is when you're exerting a periodic force on an object and that starts making the object wobble back and forth. And if that periodic force has a certain frequency called the resonant frequency, it has the ability to make the object wobble extremely. Like the amplitude of the motion will be huge. Um, there's physical examples of this. That there was a bridge in the 40s that collapsed, and one theory behind why it collapsed is that the wind was blowing on it, and basically the resonant frequency for that bridge, and it just made the bridge start wobbling, and this was observed that the bridge was very wobbly before it collapsed, and then one day the wind was just so strong that it finally collapsed. Um, anyway, we can see sort of what this phenomenon here because, right, where are we again? What we get is our particular solution has this vector c in it, and this c is like this vector that's times this periodic part. So if this vector x is representing positions of objects, and the vector c has very large numbers in it, then that means that the positions, like the numbers that are in C are the amplitudes of the objects that are wobbling back and forth. Um, and omega is like the frequency with which, or I shouldn't say frequency, it's the period with which they wobble back and forth. Um, so a vector C with very large numbers in it causes motion with large amplitudes, so like a lot of motion. And what we just saw was that these values of C have things in the denominator that are a bit disturbing. For example, these things in the denominator that could be zero, like if omega was 5 or 10, this would be undefined. And so, okay, maybe we shouldn't worry about that because undefined is just undefined. But if omega is very close to 5, then I'm dividing by a number that is very close to 0, and that gives me a huge number. So as omega approaches and now I'll use the word resonant frequency um, of either 5 or 10, you're dividing by a number that's nearly 0, and that causes C1 to be huge. And by the way, it would also cause C2 to be huge. C2 has the same stuff in the denominator. And then you see huge amplitudes. And that's basically what this graph is showing, that how the amplitudes basically blow up as you approach 5 or 10. So that's neat. And I think I'm now done with 7.5.